Hello, everyone. Welcome to the Analog Electronic Technology course. Today, we'll explore the Class AB Complementary Symmetry Power Amplifier. When learning about the Class B Complementary Symmetry Power Amplifier, you might have two questions. First, we previously mentioned that a bipolar junction transistor, BJT, is inherently a nonlinear device, and only under small signal conditions can it be approximated as linear. Since this circuit operates under large signal conditions, does that mean it suffers from severe nonlinear distortion? Second, this circuit does not include a quiescent operating point. It relies entirely on the input signal to drive the BJT into conduction. So, does the dead zone before the base emitter junction becomes forward biased affect signal amplification? For the first question, this circuit is essentially composed of two common collector amplifier stages, each with deep voltage series negative feedback, which significantly reduces nonlinear distortion. As for the second question, the dead zone of the PN junction does cause distortion at the crossover point between the positive and negative halves of the output waveform. For silicon BJTs, noticeable base and collector currents only begin to flow when the base emitter voltage exceeds about 0.6 volts. Therefore, when the input signal's absolute voltage is below 0.6 volts, there is essentially no output, leading to distortion in the output waveform. This type of distortion is known as crossover distortion. To eliminate crossover distortion, it is necessary to set a proper quiescent operating point for the two transistors. However, this bias point only needs to be high enough to overcome the dead zone. Any higher and the circuit's efficiency would be significantly reduced. The simplest method is to add a branch with two forward-biased diodes on the base side. We can use the constant voltage drop model for analysis. In the static state, the two constant voltage drops of the diodes provide the base emitter junctions of the two transistors with a small forward bias. This puts both transistors into a slightly conducting state with equal, small quiescent collector currents, and there is no static current through the load. When an AC input signal is applied, the constant voltage drop model of the diodes can be treated as a short circuit, allowing the signal to pass smoothly to the transistor bases. Because a small static bias already exists to overcome the dead zone, the signal can immediately cause output changes. Due to the presence of this initial bias, the circuit is classified as a Class AB power amplifier. In practice, a more common Class AB complementary symmetry power amplifier looks like this. The input signal is first amplified by a driver stage bilk with T3, and then passed to the final power amplifier stage. Assume that T3 already has proper static biasing, not shown in the diagram. The two diodes serve a similar function as in the previous circuit. By adjusting the resistor values of RE3 and RC3, the potential between the two diodes can be set to 0, making the upper and lower halves of the circuit symmetrical. The disadvantage of using diode biasing is that the bias voltage is not easily adjustable. Instead, a VBE multiplier circuit can be used to replace the diodes for biasing. Ignoring the base current of T4, we can derive an approximate expression for the voltage between the collector and the emitter of T4. Since VBE4 is a forward conduction voltage, it can be approximated as a constant. Thus, by adjusting the resistor ratio of R1 to R2, we can control the VCE4 voltage, thereby adjusting the bias voltage of T1 and T2. Once R1 and R2 are set, VCE4 becomes fixed, and can also be approximated by a constant voltage drop model. Although this Class AB power amplifier circuit includes a certain amount of quiescent bias, the quiescent current is very small, so the static power consumption can be considered negligible. As a result, the power-related parameters can still be estimated using the calculation formulas for Class B power amplifiers. Based on the circuit shown above, if we set -VCC equals 0 and insert a large capacitor C between the output terminal and the load RL, we get the single supply complementary symmetry circuit shown below. As shown in the diagram, when the input signal is 0, if the potential between D1 and D2 is set to half of VCC, the symmetry between T1 and T2 ensures that the voltage at point K, Vk, which is also the voltage across capacitor C, is approximately half of VCC. When a signal is applied, during the negative half cycle of the input signal Vi, the collector of T3 outputs a positive half cycle, turning T1 on, which causes current to flow through RL, charging capacitor C and delivering a positive half cycle to the load. During the positive half cycle of the input signal, the collector of T3 becomes negative, T2 conducts, and capacitor C, previously charged to half of VCC, discharges through the load RL, producing a negative half cycle at the load. As long as the time constant RLC is large enough, the capacitor C and a single power supply VCC can effectively replace the original dual supply configuration, plus VCC and minus VCC. It is worth noting that in the single supply complementary symmetry circuit, since the operating voltage of each transistor is no longer the full VCC but only half of VCC, the previously derived formulas for calculating PO, PT, PV, and PTM must be adjusted accordingly before use. The adjustment is straightforward. Simply replace VCC with half of VCC in the original formulas. This circuit can operate under a single power supply with minor modifications. The main change is the insertion of a large capacitor in series between the output and the load, and the negative power supply terminal is replaced by ground. By adjusting the resistor values in the left branch or the quiescent operating point of T3, the voltage between the two diodes can be tuned. In the static state, when power supply VCC is connected and the transient charging of capacitor C is complete, the voltage between the two diodes and the voltage at point K both equal half the supply voltage. At this point, the voltage across capacitor C is also equal to the static voltage at point K, i.e., half the supply voltage. During operation, when the input voltage Vi is in its positive half cycle, T3 outputs a negative half cycle, causing T1 to turn off and T2 to conduct. Capacitor C discharges through the load, producing the negative half cycle waveform at the load. The voltage stored in the capacitor, half the supply voltage, effectively acts as the negative supply. As long as the discharge time constant of the circuit is much larger than the longest period of the input signal, the voltage across the capacitor remains nearly constant, thus ensuring the amplitude of the negative half cycle voltage at the load. When Vi is in its negative half cycle, T3 outputs a positive half cycle, turning T1 on and T2 off. The circuit delivers the positive half cycle output to the load while briefly charging the capacitor to replenish voltage lost during discharge. Because in single supply operation the transistor voltages are roughly half of those in dual supply operation, all power-related formulas should use half of VCC in place of VCC when calculating power metrics. Previously, we discussed the Class AB BJT single supply complementary symmetry circuit. Now, let's briefly introduce the Class AB MOSFET dual supply complementary symmetry circuit. This circuit is a Class AB complementary symmetry power amplifier constructed using MOSFETs. The N-channel MOSFET T1 and P-channel MOSFET T2 are both configured as common drain amplifiers, responsible for outputting the positive and negative halves of the signal, respectively. The current sources T3 and T4 form a quiescent bias branch, generating a fixed voltage difference VGG that provides appropriate static bias to T1 and T2 to eliminate crossover distortion. The input voltage Vi is the output from the previous stage. By adjusting the DC level of Vi, the static voltage between the sources of T3 and T4 can be set to 0, ensuring symmetry between the upper and lower halves of the circuit. Assume that the transconductance parameters of T1 and T2, as well as T3 and T4, are equal, and that apart from differing width-to-length ratios, T1 and T3, both n-channel, share the same parameters, and likewise for the p-channel pair T2 and T4. Further assume that T1 through T4 operate in the saturation region and ignore channel length modulation effects. Then, based on the saturation region characteristic equations and the gate-source voltage relationships of the left and right branches, the static currents in T1 and T2 can be derived in relation to the current source IREF. It can be seen that by properly setting IREF and the width-to-length ratio of transistors T1 and T3, a small quiescent current IQ can be designed to keep T1 and T2 in a lightly conducting state. Once IREF is determined, VGG becomes a fixed value. The constant voltage drop model can similarly be used to analyze the circuit's dynamic behavior. Since MOSFETs operating in the saturation region require the drain source voltage to be greater than the difference between gate source voltage and threshold voltage, the saturation voltage drop of T1 and T2 is generally higher than that of BJTs, which means the maximum output voltage amplitude is farther from the power supply voltage. 1. Due to the presence of a dead zone voltage in the input characteristics of power BJTs or MOSFETs, a Class B complementary symmetry circuit will exhibit crossover distortion. The way to overcome this is to use a Class AB, near Class B, complementary symmetry circuit, typically biased using diodes or a VBE multiplier circuit. 2. Because complementary symmetry power amplifiers incorporate deep voltage negative feedback, even under large signal conditions, significant nonlinear distortion caused by transistor nonlinear characteristics does not occur. 3. In a single supply complementary symmetry circuit, when calculating output power, efficiency, transistor dissipation, and power supplied by the source, the formulas for the dual supply complementary symmetry circuit can be used with the substitution of half of VCC for the original VCC. That concludes our lesson on the Class AB complementary symmetry power amplifier. See you.